Okay, hello everyone. We're going to finish off our discussion of Chapter 5 with just a few applications of the determinant. There are many, many applications, but I just want to focus on a couple just to give you an idea in terms of, maybe where some of the stuff is used. The first one is the notion of what's called an adjoint of a matrix, and arguably this comes up in a more abstract setting later on, right? So what I'm about to show you is useful, but it's not the real use for the adjoint matrix. It occurs in more theoretical mathematics and more theoretical physics as a very useful tool. But I wanted to expose you to it at least, so you've at least heard the term. All right, so remember how we computed determinants using cofactors, right? So you start, let's say, with a 3x3. So I'll just show you on here. You started off, you had a 3x3 matrix A, B, C, D, E, F, G, H, and I. And suppose you wanted to use the second row, right, to guide you in your thinking. Then what you did was you multiplied the entry times -1 to the power that was equal to the sum of the row and column it was in. That's 3 in this case. And then you took the determinant of what remained if you were to throw out the row and column containing that entry, right? And so you had this, right? And so this here was the cofactor. It's C12, right? It's the one that's obtained by using, C21, pardon me. C21. It's because that this entry was in the second row, first column, right? And so that is what these numbers become here, all right? And then you added to this E times -1 to the fourth times the row in the column containing that E, which gave you AG, and so this should have been CI and BH. Sorry about that. All right, and so this is AG and CI. You always throw out the row in the column containing the entry, not the first one always. All right, and so this guy here is another cofactor. It's C22 because it comes from the position of that guy. And then you add the third one, F times -1 to the fifth, times the row and column containing that guy, which is ABGH. All right, and so this is C3, third row, third column, 3, 3. All right, I think, right? No, second row. Geez, off today. Second row, third column. Okay, and so these cofactors are really what's helping you compute the determinant, right? And so what the adjoint is going to allow us to do is gather them all together into a single matrix, right? So if I define those adjoint or the cofactors in that way, then the adjoint of A is the transpose of the matrix that combines all the cofactors, right? And so here, if you were to compute all of these cofactors, right? So the C11 would be the one using that guy, and the C21, C22, C23 is the one using this row like we just did. And then C31 and C32 and C33. This is the group of all possible cofactors used to compute the determinant of this guy. And what the adjoint is, so back to the original matrix A, if this is my matrix A, what the adjoint is the transpose of that matrix. Okay, and the reason there's a transpose there is so that certain things that we want to have happen work out nicely when computing determinants and inverses. But that's how we define the adjoint. All right, so let's go through, right? And note that if I define the adjoint in this way, then the inverse of A is equal to that nice compact formula, right? So it's 1 over the determinant times simply the adjoint of A, right? And so if we have the adjoint, then the inverse is very easy to compute. Of course, that begs the question: how do you get the adjoint easily? And we're not going to talk about that, right? So let's just, for illustration purposes, let's go through and compute all of the cofactors. This will be helpful with just finding determinants anyway. So we want, this is a 3 by 3, so we want C11, C21, C31. Let's go through and compute these. Right, so we have -1. Remember, we don't multiply here by the actual numbers in the matrix. That's only when you're computing the determinant of that matrix. The cofactor is just -1 to the correct power times the determinant of what remains if you throw out the entry in the matrix that corresponds to this position. All right, so we have -1 squared to the third and to the fourth. And then the determinant here, remember, you throw out the row and column containing that guy, the first row, first column. So -1, 2, 1, -1, and you get -1 if you compute that. Same way here, if you throw out the row and column containing the second row, first entry, right, you're going to get the determinant of 3, 1, 1, -1. That turns out to be 4. And then same way here, C31, I'm going to throw out the row and column containing that guy. And so I have 3, 1, -1, 2. Its determinant multiplied by -1 to the fourth is 7. All right. And then you keep doing this. C12, C22, C23. This is -1 to the third, -1 to the fourth, -1 to the fifth. You multiply by the right determinant. So I'm in 1, 2. This guy here, I'm going to throw out the row and column containing it. So I get 1, 2, 1, -1. That gives me a 3. And then if I just keep doing this, you can, why don't you do this on your own and check yourself with what I'm doing here. Just tedious, but it's always the same process. Okay. And then I'll cut to the chase here. C13, C23, and C33. If you go through the same process, you get 2, 1, and -5. All right. And also, let's see, the determinant of A. Remember what you can do. You could choose any row or column you want. You just multiply the entries times the correct cofactor. And so what I'm going to do is I'm going to use the first row, right? And so the determinant is the entry 2 times the cofactor C11, right? It's, remember, because that's the row and column, the determinant of row and column obtained by throwing out that guy, plus 3 times C12 plus 1 times C13, right? It's just notation here, right? If you were to write out those actual values each time around here, you would find that that's how you computed the determinant. I'm just labeling them as with the Cij notation here. And we've already computed these guys. So this is -2 plus 9 plus 2. That gives me 9 back. Okay. All right, so I have the determinant. I need the adjoint of A, right? So let's write down what C is. C11 is -1. C21, that's the next entry in that first column, 7. 3, -3, -3, 2, 1, -5. It's that transpose. Excuse me. And so I'm going to make the first row the first column, second row the second column, and the third row the third column. Right, so there's my matrix C transpose. That's the adjoint. And so therefore the inverse by our formula above is that guy times a ninth. Right, because it's 1 over the determinant. So it's 1 over 9 times each of these entries. And so I have -1/9, 4/9, 7/9, 3/9, which is a third, -3/9 is 1 -1/3, same way, and then 2/9, 1/9, and -5/9. All right, so we didn't have to go through row operations to whittle down A to the identity matrix on the left and the inverse on the right, right? So just a matter of picking your poison in some sense. This is just a justification in terms of why this works, and we can kind of see it. I mean, that's kind of what I was motivating the whole discussion by, right? This is just a compact way of writing down what you already know how to do when computing a determinant. All right. In terms of the next application, sorry for the paper change here. The next application is something called Cramer's rule. And you might have encountered this in high school algebra 2 when you solve systems, right? So there, certainly you learned elimination, substitution, and eventually a graphing technique. But there's another one called Cramer's rule that allows you to compute determinants and use those guys to find the solutions, right? So basically where the formula comes from is this, right? So you have a, sorry, it's like a paper scramble. All right. So you have a system, AX equal to B, that you want to solve. And remember, A is A11. I'm going to track the ijth or the ith column eventually. So A1n. And then here is, this is the jth row. So AJ1, this is AJI, AJN, and then all the way down to the nth case. All right, so there is our n by n matrix, A, and I multiply this by the components of my unknown, and that's equal to that right-hand side vector. All right, so there is the system that we want to solve, and now we know how to solve it. Right, you just take the inverse on both sides, so, and multiply by the right side. Right, so we know that we do that. The thing is, I know how to compute this now in terms of the adjoint, right? So this is equal to 1 over the determinant of the original matrix A times the adjoint, right? And the adjoint of A, if you remember, is the transpose of the cofactor matrix. And so here I have C11, C12, no, C21, pardon me, C31, C12, C22. I've already computed the transpose here. C32 and C13, C23, and C33 times B1. Oh, well, diddly D. Sorry about that. This should be, I'm writing it for a 3 by 3. It should be for an n by n. So C11, C21, CI1, N1. And then this goes down here to CIN. That's all I really need anyway. Okay, so C1N, CNN. All right, and I multiply this times B1. I'm going to look at BI, BN. And that's times 1 over the determinant. Sorry about that. So it's good that you didn't actually see me mess that up. So all I did here, just to recap, the solution, we took the inverse of both sides, right? So it's the inverse of our matrix A times that right side. But I know a formula for the inverse using the adjoint. Namely, it's 1 over the determinant of the original matrix times the adjoint matrix times the right side's already there. And so what I want to do, if I want the xi, so if I want the ith component of the solution vector, well, remember this is going to be the ith component of what you get over here. And so what you'd have to do to get that is multiply the ith row times the ith column. So I should have multiplied, I should have actually written out the row. So this is C1i, C2i, CNI. That's what I'm going to need there. So this is the ith row, and then I'm going to multiply by that column times 1 over the determinant. And so I have 1 over the determinant of A times C1i times B1 plus C2i times B2 plus CNI times BN. Okay, but this is precisely what you would get if you were computing the determinant of what I'm going to call A sub I. And all A sub I is the matrix A with the ith column, that should be an I, the ith column replaced by B, right? So if I replaced here B with that column with my right-hand side matrix, that is what I'm calling A sub I down below, right? And that is its determinant using cofactors. All right, and you can do this for every component. It's just that for every component you want to get, you have to replace that particular column of the original matrix by this right-hand side. All right, and so this is true for all I. You can get the components of the solution vector just by computing determinants of the correct matrices, which is kind of nice, right? You don't have to find inverses at all. You just whittles everything down to computing determinants. All right, and so let's see how to actually use this on a simple example. All right, so let's look at this guy here. All right, so we have, let's actually rewrite this in matrix form. We have the matrix 4, 1, 3, 2. That's our A matrix, x1, x2, and our right-hand side is 5, 7. Okay, so this is our matrix A, this is our matrix B. And what Cramer's rule tells us is as long as A is invertible, if A is not invertible, there would be no solution anyway, because technically you have to multiply both sides by A inverse to get the solution, right? So, but notice the determinant of A here is just 5, right? 4 times 2 minus 1 times 3. So we're good with the invertibility. All right, so by Cramer's rule, x1 is the determinant of A1 over the determinant of A. But remember, A1 is the matrix obtained by replacing the first column of A by that right side. And so I want to replace 4, 3 by 5, 7. The 1, 2 stays there. Its determinant is 10 minus 7, which is 3. And so 3/5 is x sub 1. Nice. And then x2, you do the same thing. That's now the determinant of A2, but A2 is the matrix obtained by replacing the second column of A by that right side. Keep the other one the same. Over to the determinant of A, let's write that here, determinant of A, just so you know each time what you're doing. The bottom never changes, it stays 5. 28 minus 15 on the top is 13. And so right there, we have the solution, right? The solution is the ordered pair 3/5, 13/5. Right, so Cramer's rule is actually kind of useful in that regard, right? It gives you a solution rather quickly. All right, and this I already talked about, right? So that's the justification as to why Cramer's rule works. All right, another example, the next two are really examples that arise in the calculus, especially when you're changing variables in double and triple integrals, right? So that's the primary place that they arise. Okay, so let's look at this. If you want to find the area of a parallelogram, right? Geometrically, we know that the area of a parallelogram is the length of a base times the height, but the height has to be obtained by dropping a perpendicular from one of the vertices down to the base, especially if it's not a rectangle. And so that's that's not fun. So what you want to do instead is look at this. We want to look at a mapping, a linear mapping. Remember those transformations we talked about that takes the unit square to the parallelogram, right? And so if you remember, because I want to eventually get at a matrix A. And so let's look at T of X, Y. I'm going to define a mapping who takes the unit square, right? So the unit square is here, right? And I want to map that to the parallelogram and with these vertices. Right? So the vertices, let's plot them. Here's 0, 0, 2, 3 is here. 5, 1, 3, 4 is here. And 7, 4 is up here. Okay, and so what I get is that parallelogram. All right. And so what's going to happen is you're going to map this segment to this guy. Let's map that side to that side. And let's map this guy to this guy. Right now, the reason I'm doing that, if you remember, is a linear transformation. All you need is to understand how it behaves at the basis elements of the underlying space. Well, this is in R2, and we know that the basis or a basis for R2 consists of the vectors 0, 1, and 1, 0. So if I define where T takes each of those guys, then T of everybody else has to follow in suit. All right, so in other words, everything else will preserve that geometry. And so let's do this. We want T of 0, 1 to be the vector 2, 3. And I want T of 1, 0 to, right, because that's here. And I want T of 1, 0 to be 5, 1. All right, and so you can write these in either order. I'm going to write it as 5, 1, 2, 3. But notice here, this matrix, if I use that transformation, that will take the unit square to that parallelogram. Okay, now why is that important? Well, the claim here is that the area of this parallelogram is nothing but the determinant of this matrix here. All right, so I'm not proving that. You can actually easily see it with enlarging or shrinking a rectangle, right? So if you take a square to a rectangle with longer sides and compute its area, you'll notice that the determinant of that matrix coincides with the area, right? It's easy to check that. But here, I'm just going to use the formula as is. The determinant of my matrix A is 15 minus 2, which is 13. And so the area is 13 square units. Right, that's how you can use that. And so these, again, are done with changes of variables in Calc 3. Right, so you can distort the space, change the geometry of the space to make an integral easily computable. That's the point of doing that. And then, of course, you can do this in triple integrals too, but there you need a volume, right? So you're going to take the unit cube, right? So this, I'm just going to talk generally about the idea. So here are the three vectors, right? So you have this guy, you have this face, and then, let's see. So there is the unit cube. And we only need to know what happens to the basis in R3, which consists of the vectors 1, 0, 0, 0, 1, 0, and 0, I should say the standard basis. There's infinitely many bases. But I'm going to use this standard basis. And what you want to do, if you want to find the area of a slanted box, or a parallelepiped is what it's called, right? So that means you have a box that could have all different lengths. Oops. Right, so here I would map, should have used my other colors, but all right, so I'm going to map this guy, and I could slant it. I didn't slant it, but I could have slanted it to this edge. We'll call that vector A1. I'm going to map this guy here to this edge. All right, and then I'll map this guy to this one. Okay, so just think here, I can also take that box and smush it over so that it preserves the parallel sides and faces, but it's also not straight up and down. So these aren't at right angles. Okay, and we'll call these vectors A2 and A3 respectively. Okay, And so what you would do is just define a mapping T of X, Y, Z to be equal to the matrix where you'd form A1, A2, and A3 as your columns. So you'd have a 3 by 3 vectors there times X, Y, Z. Right, and the volume of that parallelepiped would just be the determinant of that 3 by 3 matrix, the absolute value of the determinant. So I should have said that up here too. It's the absolute value of the determinant, because determinant technically could have been negative. And so if you interchanged these columns, you would have gotten the negative of what I've gotten, right? So just be careful. It has to be positive since it's an area. And so I take the absolute value. Okay, so that just gives you a little bit of exposure to some applications of determinants. Play around with the problems in that section just to kind of get a feel for these applications and maybe read about a few others. Let me know when you have issues. And then the next time we're going to start talking about eigenvalues and eigenvectors. All right, so very good. Take it easy. I will talk to you later.